Welcome to this tutorial on SymPy for beginners. In this video, we're going to cover getting started either from your browser like I'm using now at cocalc.com versus some considerations if you're going to be downloading SymPy. Then we'll talk about different ways to import SymPy and how that will impact how you use SymPy. How you import it will determine kind of how you write things, as you'll see. We'll briefly touch on initiating a SymPy session, though that will not be something that we'll use for the remainder of the tutorial. It is very handy, so you'll want to know it. And then we'll get into some more substantive material. We'll talk about an introduction to what we mean by symbolic computation, which is really what SymPy is used for, doing math and keeping things in a symbolic form. We'll discuss defining and using quote unquote symbols, which is how we refer to, what in math you would call variables in SymPy, and why we call them symbols and how to define them. And then we'll talk about, just some different things that you can do with these symbolic expressions, including substitution, factoring, expansion, and simplification of expressions. And then we'll show you how to represent an equation in SymPy and how to solve that equation. Then we'll discuss how to make a matrix and some of the things you can do with matrices. And we'll close with some examples of basic 2D plotting and graphing. So this will be a good introduction to SymPy. The link to the SymPy documentation will be in the description, so you can go into even more depth into anything that we're talking about. But with that, let's jump right in. As you'll see, I am in cocalc.com. I'm in what's called a Jupyter notebook, and I'm actually going to delete this cell by clicking it and typing on my keyboard DD, and you'll see me do that from time to time just so we have enough space. So I'm going to delete this now. Okay, so the first thing you will want to do is to get started using SymPy. And for this tutorial, I'm using, as I mentioned, cocalc.com in my web browser, the link to which will be in the description, and that already has SymPy installed. If you're following along with a downloaded IDE like PyCharm, etc., that's fine. Just make sure you separately install SymPy, just like you would any library that does not come with Python. So a link to download SymPy from the SymPy website will be in the description, though for most users you would just type into your terminal pip install SymPy, and this is just similar to downloading any other Python package. I'm going to make it in a comment because it isn't really appropriate here, but just so you see it typed out, it's pip install SymPy, and you would type this pip install SymPy not with the comment, just pip install SymPy into your terminal, and that should download it. If that doesn't work, I would encourage you just to look at the website. There's various ways to download it. But the good news is that since we're on CoCalc, it already has SymPy installed, so all you have to do is import it. And so when you import a library like SymPy, you can either import everything at once, or you can choose specific things to import. And broadly speaking, there's 4 ways to import SymPy that I want to show you. And I do think it's important to run through these all because you're going to encounter all of them as you work with SymPy and see other people's SymPy code, because people will have different preferences, and sometimes in different situations, you'll want to do things one way or a different way. So I'm going to show you all, but it's really not different from how importing any library works in Python. So if importing a library or module is a subject that you're already well familiar with just from using Python in general, you can go ahead and skip ahead a couple of minutes. But if you're still with us, that's great. Let's first do import SymPy. And now, I'm on a Jupyter Notebook in CoCalc, so to run the cell, I would hit Shift-Enter or Shift-Return if you're on the Mac. And, and as you will see, that has imported SymPy. And now that imported SymPy in general, and if I want to use something from the SymPy library, I would have to preface it with a SymPy dot in order to let the computer know, hey, I'm going to be using SymPy here, right? And so just for an example of a SymPy function, we're going to use prime, which is a fun function for returning the nth prime, so to speak. And so, and the reason I'm using that is it doesn't take any symbols yet because we haven't learned those yet. So this is just an example. But sympy.prime, and then you type in the number of which prime you want. So if I want to know the first prime, which should be 2, I would do sympy prime 1, right, for the first prime, and I run that cell, it'll give me 2, right? Or if I want to know what the 100th prime number is, I would run that. And okay, that time it worked. Okay, so sympy.prime 100, and it gives me 541. So that's fine. And so, you have your sympy function, you preface it with sympy dot, and then whatever the function is, and you take it from there. It's one way to do it. But another way, if I did not want to type sympy dot, I could give it a nickname. I could import sympy as sp. So let me do that. So import sympy as sp. And now I no longer write sympy.prime, I write sp.prime of, whatever, the 8th prime or what have you. And make sure you run it, which I guess I didn't do. So you import sympy as sp and you run that cell, and then sp dot prime now instead of sympy. If you were to type sympy dot prime here, it wouldn't work because you imported it as sp. Okay, and you can import it as whatever you want, but sp is pretty common, so that's what we are going to be using. All right, third, I could actually forego writing anything dot here if I instead do from sympy import, and then I can import whatever I need, right? What I need right now is prime, so I could do from sympy import prime and run that cell, except it's confused because usually you don't do all of these at once. So what I'm going to do is restart the kernel so that it will know to just restart everything. Okay, and now let's do from sympy import prime. Okay, and so now I don't have to write sympy dot or sp dot because I've just imported just prime, so that's great. And now I can, I don't need the sp dot anymore. I can just write, whatever, prime 9 or what have you, and it will know because I imported it already from sympy. So when I run the cell, it's going to give me as my output the 9th prime, 23. Okay, and so this is great if I know that I only want to use prime, but what if I then say, now I want to use sympy's square root function? Well, I need to import that again special. So I would do, up top, I guess, from sympy import sqrt. Okay, and then if we run that, and now we have, we can do prime, we can do sqrt of 3 or what have you. And there it is, radical 3, because we've imported square root sqrt directly from sympy, so we don't need sympy dot or anything like that. So you see one disadvantage here is if you're not sure what you're going to use, you just know you're going to use a lot of different stuff. It might be annoying to go back and say, well, now I need to import this, now I need to import that. So another way that you could do it is you could just do from sympy import star, or from sympy import all, which is represented by this asterisk. And if you do that, then you've imported everything from sympy. So you have prime, you have square root, you have whatever it is that you want, right? And that can be very useful, and you're going to see this a lot, but we're not really going to use it in this video, and it is fraught with peril. And there's just a couple of disadvantages. And one is that you're importing a lot of stuff that you're not going to use, which isn't necessarily a best practice, but even more practically, there's just a lot of overlap between function names in SymPy versus function names in other libraries. So, for example, let's compare the SymPy library to the math library really quickly. And I'm going to restart the kernel again because it's going to get angry with me if I'm re-importing everything. So let's just restart the kernel with this refresh button. Okay, and so let's import SymPy as SP and import math as M. Okay, so we'll run that, and it's imported. So now I've imported SymPy and I've imported the math module. Okay, so let's compare here. We have, let's do a couple. Let's do sp.py, that's SymPy's pi, and let's do m.py. Okay, that's math's pi. And when we run, when we run all these cells, now you see it's two completely different things. These are both functions, these are both, I guess, constants called pi, but SymPy, it's symbolic. It keeps it as a symbol. It keeps it just as this Greek letter pi, uh, which contains the value of pi, versus the math module will spit out this numerical approximation of pi. And so, and there's others, and these have the same exact name. So if you just imported everything from SymPy and you import everything from math, it would be very confusing. You wouldn't know which one you're necessarily referring to. And let's do one more. Let's do sp.factorial 4, and we'll run that. Okay, so 4 factorial, which is 24, and then math, or m.factorial 4, which is also going to give you 24. But you see the output looks totally different, and that's because SymPy, on CoCalc anyway, has this very nice LaTeX printing. Not necessarily the case for whatever you're using, but we'll get there when we talk about printing in a little bit. But for now, you see it actually is different. That SymPy is giving us a different type of output than the math, even though they're both called factorial and even though they're both 24. It's a different thing. One is the SymPy function and one is the math module's function. So because of that, it's not necessarily the best idea to just do from SymPy import all, as we saw. And actually, you know what? I'm just going to tell you now. If you're not getting like this nice LaTeX printing 24, maybe what you're using doesn't have it, but you can do something called sp.init printing, and that's going to give you the best possible printing. So that's just a handy thing. It's not going to have an effect if I do it because we're already on the best possible printing. It'll run it, but I don't think it'll impact anything. But if you are working on something that has the LaTeX printing available, but you're not getting that 24, or that looks like it's a nice image, then you can do that if you want to get a better printing. Okay, and so if you had just imported all from these libraries and then wrote pi or wrote factorial, you wouldn't know what you're getting. So that's why in this tutorial we're going to be doing the import SymPy as SP and sp.sp. One last thing I want to show you is something called initiate session. So let's do this. Now we have okay, and then say you have import SymPy as SP, but then if you do sp.init underscore session, all right, if you run that, it's going to do a lot. This is a nice shortcut. It does a few different things. Of note, it does from SymPy import all. So from here on out, you would just do like, whatever factorial of whatever it is. Sorry. And it'll do it for you, right? It'll give you that 6 because you've imported everything from SymPy, so you no longer have to do sp dot. So that's a caveat there. And it'll define some symbols, which we'll talk about later. And it also does that init printing that I mentioned before. So that's a nice handy thing, and you'll see that a lot. But what we are going to do today, especially because I want to walk through everything step by step here, especially defining these symbols and how that all works. And I want to be clear in the tutorial when something comes from SymPy by having the sp dot in front of it. So for purpose of this tutorial, we're not going to be doing this init session, but I did want to show it to you just so you know about it, but we're not going to be using it. And so I'm just going to delete everything out and restart the kernel again so that we can start. I believe this will be the last time we ever restart the kernel in this session. I know we've been doing that a lot, but I wanted to show you different ways to import SymPy, and I don't want it to get angry with me. So I'm just going to restart the kernel one last time, and then we'll start completely afresh. Okay, and so those of you who already knew importing and skipped ahead, this is where we're going to jump in to our first substantive topic, symbolic computation. So SymPy is a library used for symbolic calculation, and that means that in SymPy, expressions are kept in their symbolic form. If you watched the section on importing, we've already seen some examples of this. So we saw pi, we saw square root of 7 staying as radical 7, but let's just show you import SymPy as SP, and then if we do SP dot, square root of 7, it will just show you radical 7, right? In the symbolic form. And that's a big advantage to SymPy, unlike, say, your pocket calculator, which is just going to start splitting decimal values. It's just going to start spitting decimal values at you. With SymPy, you can continue to manipulate expressions in a symbolic form. So if I wanted to multiply the square root of 7 times the square root of 8, it's easy. I can just do sp.sqrt 7 times sp.sqrt 8, right? And it will go ahead and do that. It'll even simplify it a little bit just on its own. Okay, so now it's 2 radical 14. Easy peasy. All right, and this symbolic form extends to things like fractions. For fractions, the function in SymPy is rational, sp.rational, like so. And you would do, so for example, 3 comma 4 would be 3 over 4, right? Versus like if you were just to write it in normal Python and did the 3/4, it would give you 0.75, but the sp.rational gives you 3 over 4 in this symbolic form. Okay, so this has a big advantage because if you wanted to do sp.rational 3 comma 4 plus, so say you want to do what's 3/4 plus 5/6, right? Sp rational 5 comma 6. It's going to add them and keep it in this symbolic form. It's going to keep it as a fraction versus if you just did this, in normal Python without using SymPy, it would give you, this 1.583333, etc. It's going to give you this decimal. So what about multiplying? You can do that too. You can do anything. It's going to keep it in the symbolic form, right? 5/8, 3/4 times 5/6, and it gives you 5/8. It keeps it in that symbolic form. Of course, sometimes you will want to know the numeric value, right? So if you want to know the numerical value, that's fine. You can do that in a couple of ways. One is to get the numerical value of whatever symbolic expression you had most recently. In our case, that was 5/8, and you can do that with a function called capital N, sp.n, and then you put an underscore inside these parentheses as, kind of your way to say, well, what's the most recent thing that we did? And it will give you that 0.625, right? And so that's 5/8 in a numerical form, right? Because 5/8 is 0.625, but this time it gave it to you because it showed you this is the most recent thing. All right, so you could do that. Or you can also put inside the n whatever it is that you want. So you can do sp.n of, 3/4 or, of sp.rational 3/4, and that will convert your 3/4 into a 0.75, right? Or you could also do this with, like you can choose how many digits you want. So if you do sp.n, sp.sqrt 7, if you say you wanted this to with 3 digits in it, you just do a comma 3, and it'll give you these 3 digits, 2.65. Or if you wanted like 100 digits, right, it'll give it to you with 100 digits, no problem. Okay, so that's sp.n, and you can choose the number of digits. So if you're doing like pi to, 5 digits or something, right, and it'll give you pi with 5 digits, because that's your second argument is the number of digits. You can also put at the end of your SymPy expression eval f parentheses, and so that would be, for example, sp dot sqrt 2 dot eval f. Okay, and if you run that, it's gonna also spit out, instead of radical 2, it'll give you this in a decimal approximation of radical 2. And this .lf is saying to evaluate the expression, spit back a number, so that's what it's doing. And again, you can control how many digits you want just by putting a number inside these parentheses. So if you wanted this to be 3 digits, now it's 3 digits because you put a 3 inside these parentheses. Let's do one more example and just throw in everything that we've learned so far. Let me clear out some of this junk. And I'm just clicking the cell and hitting DD to delete, just so we have more space. Okay, and so we have import as SymPy as SP, and let's do sp.pi plus sp dot square root of 2 times rational 3, times sp dot rational 3 over 4. Got there in the end. 3 comma 4. And so what's this? This is going to remember the order of operations. It's going to do 3/4 times radical 2 plus pi, right? So when we run it, let's see what it gives us. You see this? It gives us a very nice 3 radical 2 over 4 plus pi. It understood this. It applied the order of operations. It made it look really good. All right. And so let's make a variable called expr, short for expression. You'll see that a lot when you're working in SymPy. People like to use expr to mean expression. And we'll do expr equals, and so that's just saying, this is our variable name. The equal sign says, okay, well, what are we going to store inside that variable? We're going to store some expression, and so let's go ahead and do this. Let's just copy paste it so that we're storing the same expression in there. All right, so now we've stored this expression inside our variable expr. Let's go ahead. If we were to run expr, you'll see we get the same thing. Okay, and if we were to do n or sp.n expr, okay, so that's saying, okay, I want this in numeric form. It can do it no problem. It'll just evaluate this and give you, like, as if you were punching it into a calculator, right? Or to 5 digits, it'll do it just fine. Okay, or you can do expr.evalf to, 6 digits. It does it just fine. Okay. So finally, let's just run expr again, so that it's the most recent thing, and then we'll do sp.n underscore with 100 digits, and that's saying, okay, the most recent thing, evaluate it to 100 digits, and it does it no problem. Okay, there, look at all those digits. Okay. So that's symbolic computation in a nutshell, but SymPy is even more powerful because we can define and use our own symbols. What in mathematics would normally be called variables, like x plus 1 equals 3, and you would say solve for x is a variable. But remember, in Python, the word variable already has a meaning. It's these things like expr, where you're storing data, okay? So where you're storing this data inside this variable. So you can't really call it a variable. So instead, in SymPy, we call it a symbol. And just to make it even more complex, a symbol is actually also a programming variable, and we need to define it in order to use it. And so there's a few different ways to define symbols, and you're going to see all of these as you continue with your SymPy endeavors. And so I'm going to show you a bunch of different ways, though I'll also point out which one I like the best when we get there. All right, so we have SymPy imported as SP, and there is a few different ways. One is the function symbols. So you list out whatever symbols you want to use. Let's go with x and n, okay? And so that's like solve for x, solve for n, right? So x comma n equals, all right? So to say, okay, now what am I going to be assigning into these variables? Well, I'm going to assign SymPy symbols into them. So sp dot symbols in quotes x space n, right? And so that's one way to do it. Now, if you run this, now you have the SymPy symbol x stored into the variable x, and the same n stored into n. It does not have to be the same, but it really, really should be. It's pretty rare that you'll see it not be a match, because otherwise it would just be confusing, right? So now I can do, all kinds of things. I can do x over n, and all of a sudden now I have x over n, okay? Because it's basically saying, okay, the SymPy symbol x over n is now what I'm representing with this variable x over n, okay? And or I can do something even more interesting. I can do sp dot sqrt n plus sp dot sqrt n minus 2 all over x minus 3. Okay, and you see it does it. So now I've got this radical n plus radical n minus 2, over x minus 3. Works great. You see it's my expression maintained in symbolic form, written in a little bit more of a clean way. It's good. So here's a couple other ways to do symbols. Let's keep these symbols, but let's show you one more way. Well, actually two more, but let's show you one more first. Let's do a equals symbol with a capital S. A, okay, and that's kind of a good way to do a symbol one at a time. And now I have, well, sp dot symbol A. Okay, A equals sp dot symbol with a capital S, parentheses, quotes, A. Okay, and so now we have A at our disposal. So you can do, A plus 1, right? Or you can mix and match, even though these were imported in different ways. They're all in play. A plus x plus n. There doesn't have to be a space, but there can be, minus 9. And it's all there for you. Okay. And finally, you can do what I actually think is probably the best way to do it, and is probably the way we're going to do it going forward. And that is to import the symbols directly from a part of SymPy called ABC, which has at the ready every Latin Greek alphabet letter to be a symbol. So you do from sympy.abc import, and then any Greek or Latin letter. So you can do P, Q, and Xi. And so you run it. Okay, and so now you have these imported, and now you can put it all together, and you can use these numbers, so we can do Xi, that's a Greek letter, plus P divided by 3 times A times SP dot SQRT minus 9, so let's see what this looks like. Okay, so you see, and it was able to do it. So, and we have our Greek letter here, we have the P, we have the A, we have the N. We imported these in all different ways, but we ultimately have them all. Okay, so all the symbols are in play. It does not matter how they were imported. They're all here for you. Okay, so now, normally you're going to want to just go ahead and import a bunch of symbols up top. You're probably going to know what you want to use. So what I'm going to do is, instead of this mess, I'm going to just keep from simpy.abc import, and let's go with a, b, h, n, q, p, n, q, x, y, z, and yeah, let's just do that for now. We can do more if we need them, but I think that should be fine for this tutorial, and I'm just going to rerun this. Okay, and so now we've got a bunch of symbols at the ready that we'll use for the remainder of our tutorial. All right, so let's go ahead and put this to a practical application by setting forth a formula and then substituting some values into that formula. Now, you may recall that the area of a triangle is 1/2 base times height. So let's make a variable called area, and let's store inside that variable sp rational 1, 1 comma 2 times b times h. Okay, so that's 1/2 base times height. And if we run it, it'll just store it. Now let's go ahead and see what it looks like. So there it is, bh over 2, looks great. Because that is 1/2 base times height. So here's where things get powerful. If we can do something called substituting. We can substitute in numbers or even other symbols, and we do that with area dot subs, and then we put into this 2 arguments. First, the symbol we want to substitute out, and second, the value we want to substitute out for. So let's do area dot subs b comma 3, and that's going to say take b and put in 3 instead. So it'll be 3 over 2 times h, right? Or or however it wants to put it out, 3h over 2. So that's good. So area dot subs, and we substitute in b for 3. All right, and we could have done the same thing with h. So what if we knew the base and the height, and we want to just get the area of our triangle? Well, no problem at all. You just put the tuples into a list. So you do area dot subs, and let me just scroll up here. So you do area dot subs, and then you make a list with these brackets, and you do inside that list b comma 3, and then another tuple h comma 4. So now we're saying the base is 3. We're substituting in 3 for the base, and we're substituting in 4 for the height, and that should give us the area of our triangle. And it does. It gives us 6, which is indeed the area of a triangle with the base 3 and the height of 4. And you can also substitute in another expression. So if you were told that the base of your triangle was 1/4 of its height, for example, you could do area dot subs b comma sp dot rational 1 comma 4 times height, and then that way you are going to have, the 1/4 of the height is going to be substituted in for base, and you'll see that makes sense. You end up with this input in symbolic form as h squared over 8, and then that makes sense, right? Because if we have 1/2 base times height, we substitute in 1/4 height for base here, we'd end up with 1/2 times h over 4 times h, right? So, if you were to do like sp dot rational 1/2 times h over 4 times h, you should get the same thing. Yeah, so h squared over 8. So same result. Okay, so that's substituting in. It's a very powerful feature, and there's other ways to manipulate expressions here. One is through factoring. So you can use SymPy to factor expressions. SymPy has capabilities of finding the greatest common divisor, which you can pull out when factoring, or you can just use SymPy's factoring function to factor an entire expression. So let's go ahead and show you the greatest common divisor. It's sp.gcd, and this can take the greatest common divisor, greatest common factor of numbers and symbols, no problem. So GCD of 18 and 81, is going to be 9, right? So if you threw a symbol in here, sp.gcd of 18 times x and 81, right? It's also going to be 9 because the x is not common between the two, so it's just going to be 9 just like it was before. If they both have x's in common, if there's some shared symbols, it'll also pull that out as part of the greatest common divisor. So we have, say, we have 18 times x, comma, 81 times x, squared, and let's make it 2. Let's make it 18 times x to the fourth, and you can have spaces in here or not. And now you see the GCD is 9x squared, which makes sense because it has some x's in common. It has the 9, so that's the GCD is the 9x squared. All right, so say we wanted to factor 18x plus 81, right? So 18x plus 81. So you see, let's say we wanted to factor this. So what we know from up here, when we did this before, is that we'd be pulling out the GCD of 9. So let's try it. Let's do sp.factor, and that's the function for factoring this expression. And when we run it, you see it does it just fine. It pulls out the 9, and you end up with 9 times 2x plus 9. So that's perfect. You could also have stored this into a variable and then run sp.factor over the variable, of course. So if we wanted to do sp.factor of this expression, sp.factor of this, you see it pulls it out. So you have 18x. Well, of course, that's not an expression, that's a comma, so let's do that again. If you wanted to factor 18x to the fourth minus 81x squared, it'll do that no problem. It'll pull it out, right? So you see versus before when you had this 18x to the fourth minus 81x squared, but say you were just going to store this into expression, and then you can do sp.factor expression, and it'll do it for you. Okay. So that's how you factor. You could also do the expression expr dot factor, and the same is true for subs, by the way. You can do dot subs parentheses. It'll work just fine. But if you do your expression dot factor with parentheses, it'll do the same thing, same result. Okay, we can also do the opposite with expand to expand an expression. So if you do sp.expand of 9 times x squared times in parentheses 2 times x squared minus 9. Okay, so if you were to expand that back out, then you're back where you were, 18x to the fourth minus 81x squared. So that would be, of course, if you were to multiply this and then this, right? So multiply, and that expands it. You can also, perhaps more practically, use expand on other kinds of expressions. For instance, something like, where you have 2 times x minus 9 times x plus 30. All right, so you might remember like FOIL, like first, outer, inner, last, all that stuff. Okay, but you don't need to do that if you can just expand it, and you can do that with sp.expand, and then you can just expand this whole expression. right? And so that's the result you would get if you were to do that first outer inner last method, that FOIL method. You can also, of course, do the expression. Let's do the expression dot expand, and it should work just fine. Actually, I think maybe the whole thing has to be in parentheses, just so it knows that's you're expanding the whole thing, not just that. So there you go, the whole thing in parentheses dot expand, and you don't have to worry about that if it's saved to a variable. So you can always let's just do this. Do expr to save it into a variable, and then you can either do expr dot expand or expand expr sp dot expand. That's going to be in there. Sp dot expand expr. Okay, and it's the same thing. All right. And so the one more thing I want to show you when along these lines is simplify, and that lets the computer make decisions for you as to how to best simplify an expression. So take some caution. It won't always give you what you want, but it's pretty smart, so can be a good option. Let's delete out all this junk because we no longer need it. So you might have noticed just from looking at some of these examples that if an expression is straightforward enough, SymPy is just going to simplify it for you when you put it in. So if we did like x to the power of 3 plus 3 times x to the power of 3 minus 18 times 12 times x plus 42 minus x. Okay, so you'll notice like this is really just a matter of adding and subtracting. You've got your x's to the power of 3, you've got sum to a power of 1, you've got some regular numbers with no x. Okay, so SymPy isn't going to spit it out as we wrote it. It's going to simplify it to some extent. So you see it gives you 4x cubed minus 217x plus 42. Okay, so looks good, but that's a relatively simple example where SymPy is just going to do it for you. If you put it in a more complicated expression, then you can use a function called simplify to simplify it. So let's make our variable called expr, and let's have expr equal some huge mess. We already have h and x defined as symbols, so let's go with parentheses x times h to the power of 2 minus h to the power of 2 over 3 times x minus 98 times x to the power of 3 plus h over x to the power of 3. And let's go ahead and put it all to the power of, h minus x minus 1. Okay, so we're storing this big mess of, just a jumbled nonsense that I just typed in into expression. And if we were to type it in, it'll probably simplify it to some extent, but it's still going to be a whole bunch of stuff. If we did sp dot simplify expr, it's going to give you something a little different. It's going to see it put it all over 3x cubed. Put this into parentheses. It made it a little neater, and so it simplified it a little bit. You don't have that much control as opposed to factor or expand that we saw before. Where you had a lot of control. Here you don't really have that level of control over simplification. It's just going to do what it thinks is best. And you can also, as before, do expr.simplify, so you'll see that too. It should give you the same thing, and it does. Okay. And just like before, I mean, even with things like this, you can do substitutions, right, where you're substituting in something for h and then it'll solve for it. You can do all kinds of things. So I just want to show you, these are just the different ways that you can manipulate these kinds of expressions. So the next thing I want to show you is how to solve equations with SymPy. And I have a whole separate video on this, so I am not going to belabor the point. I'll just put a link in the description. I almost did from SymPy import all. Import SymPy as SP, and then SymPy dot from SymPy dot ABC import, whatever we were working with, X N H P Q Z Y. I don't know, just a bunch of stuff. Okay, so just so we have a bunch of symbols to work with, you should probably put these alphabetical, but yeah, maybe I'm not giving a good example. So why don't I do that? Do that better. Let's do ABC and let's do H and X, Y, Z. I don't know. If I need more, I'll use them. But okay, so what was I talking about? Oh yeah, so solving equations. So the next thing I want to show you is how to solve equations with SymPy. I have a whole separate video on this, so I won't belabor it. But it's just like x plus 2 equals 3. Well, you would want to isolate on one side. That x equals 1, right? Because x plus 2 equals 3, 1 plus 2 equals 3. So you're solving for x equals 1, right? So if you were to write that by hand, it would look like x plus 2 equals 3, but you can't do that because equals is already taken. It's already taken by variable assignments, so that won't work. Instead, you are going to have to use something called sp.eq, sp.eq, capital E. Note the capital E, and then inside these parentheses, you put in your equation. So let's do, x plus 9, comma 8. So on the one side of what would be the equal sign, you put your first argument, right? And then comma, and then whatever would be on the second side. So that will give you x plus 9 equals 8. Okay, that's how it stores it. It's as the equation. Looks great. Notice that SymPy kept our equation in a symbolic form. It did not solve for x automatically. It kept it in a symbolic form. And so if you want to solve for x, you have to tell SymPy to do that specifically. So let's store this into a variable we'll call eqn. Okay, so now we have our equation, right, eqn. If we wanted to solve for it, you can do that a couple of ways. One is sp.solve, and so that's the function is solve eqn -1, and so that's solved for x, right? Because -1 plus 9 equals 8 makes sense. You can also do sp.solve set eqn. This will give you the same thing, -1, except it outputs it as you see, as opposed to a list in kind of this normal Python format. It gave you a set, okay, which is like a SymPy specific object, and actually solve set is what's recommended in the SymPy documentation. If there's more than one potential solution, like if it's x squared times 7x plus 51 or whatever, it can do that for you. It'll spit out both. It'll work just fine. If you don't specify a value, sp dot on the other end of the comma, it will assume that it's 0. So sp dot solve set, x plus 9. Now it's going to assume that you mean x plus 9 equals 0 because there's nothing on the other side. Okay, and just to show you, what I mean when I said earlier that these are a different type, in Python you can check the type of something with this. So if we were to run these cells, see, this is a list versus this is going to give you like a specific SymPy set, right? So that's why they say to use solve set, because it's going to be in this like SymPy format that will make SymPy a little less angry. But either will work, especially for things like this where it's a simple equation. It'll work just fine. On my video on solving equations with SymPy, I got a good question in the comments. So I'll deal with that here as well, which is how to get an equation as a user input. So you might know that when you do the input function in Python, it'll take the user's input as a string by default. SymPy is a means to convert that string into a SymPy form using what's called Sympify. That's SYMPIFY, Sympify. So if you do, let me just delete this stuff out. I'll try not to delete out the important stuff this time. I'll be more careful. Okay, so here we go. So if you do EQN equals sp.simplify. Okay, note it's not simplify with an L. There's no L. It's simplify because you're like turning it into SymPy or simplifying it. It's very clever. And then your input, and then type in your equation using x as the variable and EQ formatting, please. And that way you're giving kind of instructions because you're going to need them to type it in the right formatting for this to work. Okay, and so, well, actually, let's not do that yet because then we need to do sp.solve set EQN. Now let's run it. Okay, so type in your equation using x as a variable, EQ formatting, please. Let's give the EQ 3 plus x comma 23. So we're saying, okay, solve this equation that I'm giving you, which is 3 plus x equals 23. Hit enter. And I might need to rerun this cell because I didn't have this before. So let's do EQ. Actually, maybe I need to do esp.eq. 3 plus x comma 23. No, I was right the first time. It's EQ. So it's EQ. What did I have it as? 3 plus x comma 23. Hit enter, and it will solve your equation for you. So that's 20, right? Because 3 plus 20 equals 23. And so that's how you would get an equation solved using user input. You would just use Simplify to turn the string into a SymPy format. Okay. So that's about it on expressions. Now I want to show you a couple more things. I want to discuss matrices, and then a little bit on plotting and graphing, and then we're done. So I want to discuss matrices. I do intend to make this a subject of a whole standalone video that'll explain, multiplying matrices and other fun things, similar to what I did with, Sage Math I've already done, and so it'll be in that vein. So I do intend to make this a subject of a standalone video. I won't belabor it, but if you want to make a matrix in SymPy, what you do is, it's not super intuitive, but it's fairly straightforward once you see it. It's sp.matrix. Okay, so it's the function's called matrix, so note the capital M. And then inside the parentheses, you do brackets for a list. And then inside that list, you do another series of separate brackets for each row. So you do, whatever it is, 2, 3, 4, and then comma. Okay, so see, now this is going to be the first row of my matrix. Now let's do another row. 9, 8, 1, comma, 9, 3, 3, right? And so now when you run this cell, now you've got this nice matrix, and you can certainly store that matrix into a variable. No sweat. Let me just copy paste it. If we do A equals, this matrix, now it's stored into a variable. So if I were to run A, it will spit back out the matrix. You can pull just a row or a column of the matrix, right? So if you just remember to start counting at 0, that's like a quirk of Python, that you start at 0 for this kind of thing. So the first row is actually row 0. So if you do a dot row 0, that'll give you the first row, 2, 3, 4, right? Or a dot row 1 will actually give you the second row, the 9, 8, 1. Okay. You can get your columns, a dot col 2, okay, and that will give you this third column here for 1, 3. And if you just put in a vector, it'll assume it's a column. So if you do sp dot matrix of 1, 2, 3, so it's just one, it's gonna assume by default that it's gonna be a column. So keep that in mind. You can transpose it into a row by doing .t at the end, capital T, and that'll flip it, so it'll become a row. And once you have your matrices, you can do operations with them. Adding, subtracting, multiplying. There's special matrices, identity, zero matrices. A dedicated video on that is forthcoming. In the meantime, I'd encourage you just to look at the documentation for SymPy if you want to look at any of that, the link to which is in the description. Okay, and the last thing I want to go through at a high level is plotting an algebraic expression, just simple like 2D Cartesian plotting in SymPy. Again, this is also one where I want to do a whole video, so I won't go into too much detail, but I want to show you the basic function that's involved, which is plot. So it's sp dot plot, and then your equation. So x squared plus 2, for example. And it'll do a lot of it. I mean, if you saw my Matplotlib plotting and graphing video where there's, a million different things to do, this is much more straightforward. It just gave you f of x is x squared plus 2, and it plotted it for you, a nice curved line. It looks great. It fits the axes really well. There's a couple of things you can do. You can put in keyword arguments. So for example, comma title equals, whatever this is, f of x equals x. And to be fancy, I'll copy paste in a superscripted 2. So x squared, I just copy pasted that in, plus 2. For my title. So if you're not familiar with keyword arguments, all I'm doing is it's like a way to customize this graph. So I have the first argument here is the formula, and then a keyword argument at the end, which is title equals, and then whatever I want my title to be in quotes. I run that, and it should show up. And it does. There's my title. As you can see, let's see if I can zoom in a little bit, so it doesn't really help. But you see I have f of x equals x squared plus 2 up there, if you can see it. You know what I can do is I can zoom in on the browser. So there it is. Okay, so let's see. All right, and then you could put multiple lines on the same graph as well. Just put each one in as a new argument. So you have your first argument here, x squared plus 2, and why not make comma, and I think these have to be in parentheses, comma, x minus 1, comma, and then you can put in a keyword argument like title, my graph, or whatever you want it to be. Okay, and if you run it, now you see you have both plots plotted. I'm actually going to zoom out a little bit. So you can see you have your nice curve, you have your other line, you have my graph as your title, both on the same plot. Okay, and so that's the basics of plotting and graphing on SymPy. This really is scratching the surface of SymPy. I do hope to have more videos on other SymPy things, as I've alluded to, in the pipeline. So do subscribe if you're interested in that. And otherwise, that does conclude this tutorial on SymPy for beginners. If you got value out of it, I'd appreciate it if you could show your support by leaving a like. It really helps this channel get noticed, and I want to thank you very much for watching.